we were discussing last week about the nature of surfaces, and there are many different types of things that we have to understand about the surface. And as we know, tribology is basically surface property. So anything that happens on the surface will affect tribology. The very first one that we have to understand is about surface roughness and texture. So this is what we were doing last time. So for definition, surface texture is the repetitive or random deviation from the normal surface that forms the three-dimensional topography of the surface. So texture includes many things. It is repetitive, or it can be random deviation from the normal surfaces. So a normal surface, if you expect to be a smooth surface, but in general, or whatever roughness you are expecting, but in general you will get a surface which is not what you expected. It has got different features on the surface, then it is called texture. So texture is not just one parameter. And here in the texture, the very first thing is the roughness, whether it is nano scale or micro scale. So both are important depending upon the engineering application or tribology. So as I was saying last time, that in some cases even angstrom level roughness is very critical, and the example is magnetic hard disks. For magnetic hard disks, the roughness of the disk is in the range of few angstroms, only few angstroms. So that means atomically smooth surface. Whereas in some other cases, let's say road, you will see any road which is a newly made road has got some roughness, some texture on it, because that roughness or texture is important for the movement of the vehicle. Otherwise, the frictional property between the tire and the road will change, and because of that change, it may not be a suitable, the road may not be suitable for driving. So therefore we have to maintain a certain kind of roughness and certain kind of texture. Another type of roughness related parameter is called waviness. So waviness is not exactly roughness, but you can call it in macro scale roughness. So when we see that the profile of the surface changes in a very repetitive manner, like a wave, then we call it waviness or macro roughness. Another important part is the lay. Lay is basically when the direction of predominant surface pattern. So if surface has been manufactured in such a way that it gives this kind of feature, whether it is some sort of roughness or some waviness, but this kind of roughness or feature, it extends in one particular direction, then it is called lay, and this is the direction of lay. This is generally produced by most of the engineering processes like turning, machining. They all have this kind of lays. Then fourth one is flaws. Flaws are basically some irregularities in the surface. So for example, there can be some scratch or some depression, some pit formation. So these will be the flaws of the surface. So all together we call them surface texture. So we will go through some of the terminology and parameters that are used for surface texturing. It is not always possible to well define a surface texture, but different statistical parameters have been proposed and used for this purpose. So here is a pictorial display of surface texture. So if we talk about some sort of roughness or waviness, then looking at this surface in a very macro scale, and now looking at 2D profile still in a macro scale, then it will give us the impression of wider spacing of irregularities. So there is a depression here, there is a depression here, and so on. This is the peaks, peak here and peak, but the spacing is quite wide here. In this case it could be a few millimeter in our engineering sense. So this kind of feature which goes up and down like this in a very regular fashion, this will be waviness. Because for our engineering application, if these kind of features are in few millimeters, then we call it waviness. If we zoom into small portion of this part and look at this, then we see there is another type of waviness coming here. Here also we can see the peaks and the valleys here, but the spacing is quite close. It can be few microns, hundreds of microns in this kind of range. Then this one is more like a roughness. So this is what we mean by the roughness, and this is what we mean by the waviness. So it is a matter of scale basically. And sampling length. So for example, here the sampling length can be few millimeters to several centimeters, and here the sampling length can be hundreds of micron to a millimeter, in that kind of range. So this is how we will understand between waviness and the roughness. And the other one is lay, as we were talking about lay. So you see the roughness here or some sort of pattern here, okay? But this pattern is repeated in this direction. So therefore this one is known as lay. So this is a result of the tool. So tool feed rate, or it could be some other kinds of basically tool feed rate, how we feed the tool, and this forms the lay on the surface. So all kinds of machining processes, turning, milling, drilling and grinding will produce this kind of lay or striations. But some other processes such as casting or shot pinning or grit blasting, which produce no characteristic directions, are said to have a non-directional, particulate or protuberant lay. So for example, in shot blasting or sand blasting, you will have a surface which forms quite irregular way of or random way of depressions. So if you take a two-dimensional profile here, then you will see quite random here. Similarly, you can take this way, again you will see quite random profile. So that means there is no this kind of feature which we call lay. So depending upon the engineering process, you can produce lay on the surface or it may not be produced. So tribology has a very strong influence on how the surfaces are generated. For example, a very simplistic way will be that in the direction of lay, especially for lubricated contact, you will have low coefficient of friction. Across the lay direction, you will have high coefficient of friction. So this basically the way these features will help or not help in the sliding process. So this is a very simple way of looking at it, but there are many much more complex effects of texture. For example, a rounded texture if we talk about in x and y direction, both direction it's rounded. This kind of feature in two-dimensional, it will show you like this. This kind of feature will provide or rather help in forming hydrodynamic lubrication, because this kind of flat surface will reduce the contact stress, and also this kind of inclination of the surface will help to form some hydrodynamic lubrication when the lubricant is present. So this will help in lubrication process. So tribology will be better for this case. But compare this with another feature where you have got sharp peaks. In this case, if you are sliding, then this kind of sharpness basically increases the contact stress, and therefore the wear will be increased for this case. So depending upon texture, we can expect different tribological performance. So therefore it is important that we define surfaces. Based on that, we can perhaps get some information on by changing different surface parameter, we can change the tribology. General typology of engineering surface, so general types of surfaces that we can use in engineering. So in engineering, normally we encounter homogeneous surface. We don't encounter inhomogeneous surface. Means whatever features are there on the surface are of homogeneous type. And then we often deal with random. So among homogeneous, we deal with random surfaces. Although there are many cases where the surface features may not be exactly random, but in general we encounter random surfaces. Within the random, there are isotropic and anisotropic. So isotropic will be where the features are same in all directions, or x and y direction. Anisotropic will be when the features are not random in all direction, but rather has got some directionality. And then another terminology you will see is Gaussian surface and non-Gaussian surface. So this one we will define more clearly. So this is related to the distribution of the heights of the features on the surface. So for example, this is the roughness, and if we take the mean and we measure these heights from the mean, similarly we measure these valleys, depths from the mean, okay, and we plot the distribution of these heights and depths, then in one case it is called Gaussian when it is random. In another case it will be called non-Gaussian. So engineering surfaces are in general random, either isotropic or anisotropic, and Gaussian or non-Gaussian. So this is just a general nature of engineering surfaces that we deal with, but there can be some special cases for other types of surfaces as well. And it's basically because of the way surfaces are produced. So for example, single point cutting process, this will produce anisotropic type of surface, whereas some other like a sandblasting or even casting may produce you isotropic surface. So depending upon what kind of engineering process we follow for the manufacturing, we will have one of these types of surfaces. Effect of the scales of the vertical height and horizontal spacing features. So now one thing is, whenever you look at the surface profiles, often you will see of this type. It looks like something like this, not like this, but actually these two surfaces may be the same. Are they same, these two surfaces?
No, sir.
Why they are not same?
Sir, by inspection, sir, we can see that their both profiles are different.
In what way? For example, A and B. So A, what do you think about A?
Sir, is the we define a point which name is.
So in terms of smoothness and roughness, you will call A as a smoother surface than B.
Yes, sir, because there is less crust and trough in the surface of.
Yeah. So in visual inspection, we can see like this. But if you see this surface has got magnification of 5000 in this direction. Let's say this is X direction and this is Y direction. Sorry, this is Z direction. This is vertical. So you see the magnification is 5000 times here, but in the B, magnification is only 100 times. Okay, so that means this is much more compressed version of a surface. So it has got more compressed data. Now in the vertical, you see it has got 500 times magnification. This one has got 5000 times magnification. So that means in the vertical direction, it is more spaced, more wider. So these two surfaces may be the same. What you see is 5000, that means it may be a very small portion of the total, and this may be not very highly magnified. So therefore it looks like this. So the surfaces may be the same, but depending upon the scales that we use, you have different perception of the surface. This looks very rough, this looks less rough, but this is because of the different scales that has been used. So long back we were doing some research, and we produce AFM. So you know atomic force microscope?
No, sir, we not hear about it.
Okay, so atomic force microscope is also basically something that can give you the roughness feature, but at a very minute detail, almost going all the way to atomic scale. So if you look at the roughness, so we looked at the roughness, so it looks something like this, just like you are looking here, very sharp peaks. Okay, so this was the roughness of the surface. So obviously this surface looks very rough, and we can do some conclusion based on this. Okay, but what is important to remember is this one was, for example, 1 micrometer. This the sampling length, okay, up to here, from here to here, 1 micrometer. But on this scale, on the vertical scale, it was, for example, 100 nanometer or maybe only 10 nanometer. So on the vertical side, it is very much exaggerated, very much expanded, whereas on the horizontal side scale, it is compressed. So that's why it looks like this one. So what we did was we plotted both on the same scale. So let's say vertical also 10 nanometer and horizontal also 10 nanometer, same surface, because we have digital data. That means all data, individual point data are there, so we can do any kind of plotting. So if we plot like this, then it only shows something like this. Okay, so that means the surface was actually very smooth, very rounded and smooth, but because of the presentation of the data, it looks very rough here. So this is a very important part, and often we forget about this part, that because of different scales that are used in plotting the data, plotting the surface profile, the perception of the surface can be quite different compared to what it is in the original case. So now the data is surface profilometry data are produced by a stylus. So stylus is a diamond tip, very sharp here, and it is made to move from one direction to another. Okay. And as it moves, so it has got some device, so as it moves up and down, the electronics will record the data. So it will record both the horizontal direction x and the vertical direction data. So it will form a digital image of this one. And similarly, if we have got a 2D like this, so I can scan once here, again here, again here, and I can keep scanning. So if I scan it very small spacing, then I can generate the whole surface as digital data. This is what is done in the optical profilometer as well as the AFM I was talking just now, or atomic force microscope, where the digital data is collected in each scan. So in each scan I have got, let's say this is X and this is Y, and the vertical direction is Z. So this I'm just showing X and Y. So for X and Y and Z, all the data can be obtained. So let's say X, Y and Z, and we can record all the data. So this is how we can digitize the whole surface, and then we can use that digital data to plot any kind of graph or 3D map it quite easily, because nowadays so many computer softwares are available that can help you to plot such kind of data. So this is how nowadays we can visualize the surfaces, but along with visualization we also need some numbers, so that we can say that okay, this surface has got this number or this surface has got this number, and we can make the difference. So now going into the definition of the numbers, the first one starts with this one, RA, which you must have already studied previously. So it is called average roughness, or RA, and this used to be called before arithmetic average, and more commonly it used to be called centerline average, or CLA. So basically it is an average deviation of the individual point measurements of heights and depths from the arithmetic mean elevation of the points. So for example, here you see this is the actual roughness of the surface, or actual profile of the surface in 2D. So if we can find the mean line here, so now from the mean line we have these heights here and we have these depths here within a sampling length of L. So RA is basically different heights and the values or depths. Here we have taken absolute values, so plus and minus all are treated as plus. So within a sampling length of L, if we have n points and n points heights and depths are given like this, then this will be known as RA. So basically averaging of all the heights and depths here. RA can also be given in the form of squared, so y1 square, y2 square, so that it gives little bit slightly different values but still the same RA values. So these two are the traditional definitions of RA, and RA is a very useful number, because in most of the cases, most of the surfaces, you will see that RA is provided. Okay, no other data but only RA is provided. So even though it is true that RA is not a complete description of the texture or even the surface roughness parameter, but RA is the most used parameter. A more formal way of writing RA is like this. So within the sampling length, so Z and dx. So for example, if profile is like this and you have got a mean line, and for each Z and dx, again Z and dx, Z and dx, so you can sum them all together divided by the total length. So all the dx put together will be L. So basically you see this in the integration, this becomes L and L gets cancelled out, so it is basically finally the Z that is important here. So this is another way of defining RA, and in this way of definition it means that the area, so we are considering the area rather than the heights. So now if you look at these two profiles, 2D profiles here, so this is a more gentler sinusoidal type of profile, and this one has got more spiky nature. Okay, but both of these two surfaces has got same RA. RA is 0.64 A, where A is this dimension. So RA is the same for both. But do you think these two surfaces are the same? In our
No, sir, they are different.
They are different. In our engineering application or tribological application, what do you think they will have in terms of tribological performance?
So like in second case, lubrication is not occurs smoothly. That
Okay.
means there is a trapping of oils in between. But in first cases, there are smooth profiles, so we can lubricate them very easily.
Yes. So especially if we are dealing with lubricant or even in dry condition, we can expect that this has got smooth, some sort of lower contact stress, this has got high contact stress, and the flow of the lubricant might be better in this case compared to here, and the wear can take place from these sharp ends. Okay, so we can clearly say that tribologically they are different, their performance will be different, but if we report RA values, the RA values will be the same for both. So this shows us the problem that only RA cannot define a surface for our tribological application. So that's why there are some more other parameters which has been used. So another one is called RQ, or root mean square, which is defined by this. So basically it has been squared here and then under root. Okay. So this gives a better picture of the surface, but still RQ also has got similar kind of issue as with RA. In many cases you will have RQ as reported, in some cases you will have only RA as reported. So for some this ratio of RQ to RA is often given, and it is said that for sine wave type of surface profile this is 1.11. Then some other kinds of surfaces, for example Gaussian distribution we were talking about, it is 1.25. So these numbers have been calculated and given, but the important thing is that can RA give us a complete picture of the surface as far as tribology is concerned, or can RQ give us the complete picture? So those two are the facts. Another type of definition of the surface is what is known as abort bearing area.
Excuse me, sir.
Yeah.
Sir, you told that previous two cases are same, then we cannot define using RA that both are same surfaces.
Yeah.
That means, but sir, if RA same, then RQ is also same because this ratio are constant.
You mean RA and RQ are?
Yes, sir. If RA is same for two cases, two cases, then RQ is also same in two
Yes,
cases.
yes, because the ratio is fixed.
Yes, sir. Then again, this is the situation.
Same situation.
We cannot
Yeah.
say.
Yeah.
Yes,
So that is what I said, that RQ doesn't solve the problem, but it just gives us a little bit better homogeneous number. So that means small variations because of peaks and valleys that we can see in RA is reduced in RQ, but RQ doesn't solve the problem. So still we have the same issue.
Yes.
Yeah. So another way of giving the data is called abort bearing area. So this basically it plots an accumulated value. So for example, if this is the roughness and we start from here, so as we touch here, so we are touching only one peak here, not the rest are all below this. So we plot here this one, start from here, and as we go downwards we are touching more and more peaks and the width of these peaks. So that is how we have got this sum of A plus B plus A1 plus A2 plus A3 A4. For example, here if we were here, then there will be only a small width which will be here. As we go down, we have got more contact area, more contact surfaces, and at some point complete touch. So this is known as the bearing area, how much the area is bearing the load if you apply the load from here. So at this point only little bit, and at this point all the surfaces are being borne by the other surface. So this is another way of defining the bearing area concept. Again, this is not so much used, but perhaps this will be useful in contact stress calculation. So now we have got some numbers here which are typically given. So arithmetic roughness average, or RA. So same RA that we have just now gone through the definition, and micrometer or micro inch. Often in the US people work in inch more, so they will give you values in micro inch, but in nearly rest of the world we follow the micrometer. So micrometer is more appropriate perhaps. And here you can see that for sand casting, hot rolling, you get very rough surface. RA is very high, and as you go down for rolling bearing raceways, we have very smooth surface. So it is produced by machining process which gives a much smoother surface. Rolling elements like rolling balls, they have got even smoother surface then, because they are produced by lapping technology. So these numbers are approximate or given in the terms of range, so there is a very wide variation of the range, but for any particular application or for your own engineering application, it is very important that you report what kind of roughness you need for your application, and depending upon the roughness it will have the tribological property and other engineering properties. Some more data on RA. So for rough casting, coarse machining, fine machining, grinding and so on, lapping process or super finishing gives you much smoother surface. So these are the typical values which we need to more or less understand, but as I said, actual RA may not be the true representation of the texture of the surface, but since we don't have many numbers, we often rely on RA in terms of the data.